All right. The final method for finding the volume of a solid in this course is called the washer method. And the washer method is actually pretty similar to the disk method. All it does is really deal with situations in which one of our lower boundaries creates a bit of a gap, if you will, between the enclosed region and the boundary itself. So for example, if we look at this particular function that's been enclosed, x to the fourth, and the other function being 8x, we see that if we were to rotate this about the x-axis, for example, we notice that there's like this region here that is not accounted for. There's this kind of empty region or this empty space. And so what happens is as we rotate this about the x-axis, as we rotate this about the x-axis here, what we're going to see is that this region where there is an enclosed region here, there's going to be a bit of a shaded space. So as we rotate this around the x-axis, we're going to have a solid formed here. But in this region that's been highlighted blue, we'll notice in this region here, this entire space is going to be kind of hollowed out, if you will. So the reason why this is called the disk method is because as we rotate this about our axis, it creates something that looks like what's called a washer. This is known as a washer. It's essentially just a hollowed out disk. Okay, so I'm just going to kind of like show this here or maybe place this somewhere here to indicate that we have a hollowed out disk. And as I did in my previous lessons, I want to kind of make sure that we are able to visualize this. So let me just quickly pull up, well, there's where I got my image of my washer here. So I went ahead and slightly adjusted the two functions, so x squared and 2x. So just so we can kind of see what this looks like as we rotate around, as I rotate this about the x-axis, you can see that these disks, as I move them around, are going to have a hollowed out region. So it's almost going to look more like a cone than anything else. There's a hollowed out region. So it's not fully solid. There is going to be some hollowed out region that is based on the space in between the enclosed region and whatever axis that you're rotating this about. So this is pretty similar to what we did previously when we were finding the area in between curves. And the main idea with that concept or those types of questions were to subtract the smaller area from the larger area. If you recall, when we did those problems, we had a function like this, and we had this area here between A and B. And if I wanted to find, and then we had another function, let me just do this in red, another function here, and we have this region that we can subtract. To find this green region here, we would just subtract the larger area, which was given by f of x, minus the smaller area, which was given by g of x. If you can go back and watch my I believe it was my 4.5 video on finding the area in between curves. Well, this is essentially the same idea, but now this time with rotations. So as we rotate about a certain axis, again, we're going to be integrating from A to B. So let me just write V here. So we're still integrating from A to B, but we're effectively going to be taking the area of my larger disk. So I'm going to say pi r squared. So this is going to be the area of the bigger disk, of larger disk. And then from that, I'm going to be subtracting the area of my smaller disk, the area of the smaller, and this is going to be our hollow disk, So this is the hollowed out region here, and we're doing all of this with respect to x. So as we're seeing here, we can actually simplify this and rewrite this using integration properties. We notice that we have a common constant of pi in both of these terms. So we can say that this is pi here, integrated r squared minus lowercase r squared. Okay? So now in the context of this problem here, notice that in this problem we are integrating from 0 to 2. Okay, that's because this is the point where those two functions intersect, from 0 to 2. What is the area of my larger disk? So this is going to be, I need my larger radius here. I'm going to call this my larger radius. So that, in this case, represents the entire height of the function. Well, what is a larger function here? That would be our a to the x. That's our higher function. So the radius from the x-axis to any point along this line, 8x, is going to be our uppercase R. So uppercase R is going to be equal to 8x. So I can write this as 8x squared. Now what about our lowercase r, which is this hollowed out region here? This is our lowercase r. Well, that's going to be the distance from our x-axis to the lower function, which was x to the fourth. This is our lower function. Okay, so in this case, we would be subtracting x to the fourth, all of that squared, and this is all done with respect to the x. So you can put this into your calculator right now, and you should get 357.443, make that a little bit larger, units cubed. Okay, so as you see here, it's really kind of combining the two ideas of rotating about a particular axis using the disk method, and then just subtracting out the hollowed region. Now this can get a little bit trickier, of course, as we start looking at different types of functions and when we start to rotate about different axes, but with enough practice, I really think that this is something that can be quickly grasped. All right, let's do a few practice problems here. Let's set these up. So you may want to grab your calculator here and go ahead and work through these with me. But for the first problem here, let's graph y equals x. So I'm just going to quickly graph these. This is just pretty easy to sketch. Y equals x. And my other function is y equals x squared. So we know that they're going to intersect at 1 and 1. So I'm going to do something like this. So it's a pretty small sliver of a region here, but it's pretty similar to what we did in our previous example. Okay. So ask yourself here, what is the larger r and what is the smaller r? Well, if we rotate this about here, about these axes, we can say that my larger r is the distance up until my upper axis. So larger r is going to be, in this case, the height given by y equals x. Okay, so that we can say that for any function here, the output is going to be whatever x is. Okay, so my larger radius is going to be whatever x is. Now, what does my second function say? My second function, which is going to represent my smaller radius here, that's output is determined, y is determined by whatever x squared is. So my lower radius, or my smaller radius, is x squared. Okay, so if I needed to set up the volume here, which I'm not asking you to do for these practice problems, I'm just determining the uppercase r and my lowercase r, or my big radius and my small radius. But if I needed to, I could integrate this from 0 to 1, because that's where these two functions are intersecting at the point 1. And this would be r squared, x squared, minus lowercase r, which is x squared, all of that squared, dx. And I left off the pi. Of course I did. There we go. So that would be my integral there. Okay. All right. Go ahead and try something like this. This time we're rotating about the y-axis. So my function here, y is equal to x. So y is equal to x. So again, it's my same function. In fact, you know what? Just for the sake of time, let me just take all of this and just copy that over and paste it here. Actually, I want to paste it not as an image because I wanted to remove one thing. I want to erase this stuff here because actually this time I want to rotate it about the y-axis. So this image is going to look like it's rotated about this way. So we're going to have a solid that looks something like this, and that's probably too much. There we go. Okay, so we're going to see that this solid is rotated about the y-axis. Well, in this case, what is my larger r? Well, let's go this way this time. So let's erase this stuff. My larger radius, again, is going to be the distance from here to here. So what is my x value? My larger radius is whatever is given from this function now as a function of y. My large r, okay, is actually, and maybe it's hard to see from where this line is, so let me actually move it down here. If we go out this way, this time the large radius is determined by the x value given from this function here. So I would want to rewrite x as a function of y. So if y is equal to x squared, x as a function of y is plus or minus y. So my larger radius this time is going to be the square root of y. And we're going to square that, so it doesn't matter if it's positive or negative. Now, what is my smaller radius? Now, this is the distance, the x distance going up until the line y equals x now. So my lowercase r is going to be equal to whatever y is, because x is a function of y. X is determined by whatever y is, okay? So in this case, if I wanted to set up this volume, I would say the volume is pi. We're integrating from 0 to 1 again, but keep in mind we're going vertically up the y-axis. My larger radius is root y squared. My smaller radius is y squared, and I'm integrating all of this with respect to y, okay? So let me actually make some space so I can also do number 3. So that's what your integral would look like there, okay? All right, now number 3, I'm going to go ahead and copy and paste this function again. It's the same function, all right? But this time we're going to be rotating this. I should probably do this. This time we're going to be, that's a horrible line. We're going to be rotating this about a different line. We're going to be rotating this about the line x is equal to 5. So that was 1. If we kind of extend this out here, so 2, 3, 4, 5. So we're going to treat this as our axis. So think about this for a second. If I rotate this about x is equal to 5, this rotation, if we rotate it about this line here, we're going to get something that looks like this. So we're rotating this entire solid, and I know this is kind of hard to visualize here, but imagine we're getting this larger disk minus this, and then this is going to be super small, a little bit really hard to see here. Oops. Kind of this hollowed out region here. So that's what our disk is going to look like. Instead, that just looks like a mouth. Congratulations. Now you can't unsee it. All right. The main thing here that we need to recognize is we are rotating horizontally, okay, around a vertical axis. So what is our large R here? Our large R is going to be the distance. Let me do this in blue. The distance between this line, the line is the outer boundary here, the distance between the line and x is equal to 5. So ask yourself, what would that be? Well, we know that the horizontal distance, this r value, is going to be 5 minus whatever x value we are given. Whatever x value we are given. So we see here that x is equal to y, so we would say 5 minus whatever y is. So because this entire distance from, let me do this here, this entire distance is 5. As we move horizontally along the x-axis, we're given different x values for whatever y might be. We're given different x values for whatever y might be. If we take the entire distance of 5 and subtract one of these values from it, what's left over is this value here. Or maybe actually do this in a solid line so we can see, is this distance here. And that's effectively what we're finding. So that's going to give us our larger radius. Now, if we're going to go back now, what about our smaller radius? Well, it's the same idea. We're going to go 5 minus, and the horizontal distance given to this parabola here. So if we take the entire distance of 5 and subtract this horizontal distance from it, which we see as root y, we did that in our previous problem, that gives us our smaller radius, okay? All right, so that was most of the heavy lifting. I will do one more problem here just to make sure that we're comfortable setting all of this up. Let's do something a little bit more difficult or a little more complicated, something like y is equal to x squared, and y equals x plus 2. So if I were to quickly graph this function here, so this we have a quadratic here, and we have the line, so this is 1, 1, y equals x plus 2, okay? So 5, 3, 4. So let me actually make this a little bit neater. Something like that. And y equals x plus 2. So this would look something like this. Let's do that. Y equals x plus 2. And this is y is equal to x squared. Okay. So we have this region here. Okay. And we are going to rotate this about the line y equals -1. So let's rotate this about y equals -1, which is down here. So we are going to rotate this around a horizontal axis here. So ask yourself, what is my larger radius here? So if I rotate this around, and I can just kind of arbitrarily draw something like this, okay? This here is my larger radius. What would that be in this case? Well, my larger radius is going to be whatever the distance was from our x-axis up to our line. So for our line, our output is x plus 2. So whatever that distance is. And because this remaining distance here is 1, you can think of this as subtracting a -1, or you could just think of this as adding +1. But we know this distance here from the x-axis to this line is 1. So this entire distance, so this here was x plus 2. This distance here is 1, so we can say that x plus 3 is my larger radius. Okay? Now, what about my smaller radius here? From here to here, same idea. I know that this distance here is still 1, and this distance here is going to be the height given by my function x squared. So we can say x squared, again, minus -1, or x squared plus 1. They'll both give us this here. So I've established my large radius and my smaller radius, so I can say v is equal to, since we're rotating at about this axis here, we're going to be integrating from -1 to +2, which we can set the functions equal to each other to find those exact values, but hopefully it was pretty obvious. And our large radius is x plus 3 squared, and our smaller radius was x squared plus 1 squared. And this all again comes back from just us integrating these areas of these disks and hollow disks. Okay? And this should come out to approximately 23.4 pi units cubed. Okay?